Hello, in this video we'll be working through Unit 4 homework problems 34 through 39. For number 34, we're given the graph of a function s of t, and we're asked to decide if s prime, and s double prime are positive, negative, or zero at different points along the graph of s. So starting with point A, is s of t positive, negative, or zero? Well, we're looking at the graph of s of t, and this graph would be positive if the point is above the x-axis. In other words, the y-coordinate is positive. It would be negative if the point is below the x-axis, and it would be zero if the point were on the x-axis. So point A is above the x-axis, and that means that s of t is positive at A. Let's go ahead and stick with the graph of s and do all of the points. So point B, it's above the x-axis, so it's positive. C is above the x-axis, so it's positive. D is above the x-axis, so it's positive. And E is also above the x-axis. So the function s of t is positive at each one of those points. Now what about s prime of t? So s prime is talking about the slope of s of t. At point A, we have a negative slope. Negative. At point B, the slope is 0. At point C, the slope is positive. At point D, the slope is 0. And at point E, the slope is negative. Now, second derivative. To determine the sign of the second derivative, we want to think about concavity. So at point A, the graph is concave up. So second derivative is positive. Point B, the graph there is concave up. So second derivative positive. Point C. Now point C, the concavity is changing. So here the graph is concave up, here the graph is concave down, and C is right where it changes concavity. So the second derivative there is 0. D, the graph is concave down, so second derivative is negative. E, the graph is concave down, so the second derivative is negative. Now if you found that confusing, let's look at it one more time. If we want to know whether the first derivative, s prime, is positive or negative, then we ask if the graph is decreasing or increasing. So this graph is decreasing until we hit point B, and then it turns and it's increasing until we hit D, and then it turns and it's decreasing after point E. Okay, so our slopes are going to be negative until we hit B, that has a slope of 0. Positive until we hit D, that has a slope of 0, and then negative after that. Now in terms of concavity, this graph is concave up all the way until point C right here. So from negative infinity up until we get to point C, that graph is concave up. And then it switches and the graph is concave down after that. Concave down from point C to infinity. So concave up on the left of point C, that means second derivative is positive. Concave down to the right of point C, so second derivative negative. And at C, we have a change in concavity, an inflection point, so the second derivative there is 0. 35. If for all real numbers x, f prime of x is less than 0, and f double prime of x is greater than 0, which of the following curves could be part of the graph of f of x? So we're told f prime of x is less than 0, and we know that means that f is decreasing for all real numbers x. So we need a graph that is decreasing. And then we're also told f double prime of x is greater than 0, and we know that means that f is concave up. So we need a graph that is decreasing and concave up. That's going to be graph C, decreasing, concave up. 36, the graph of a twice differentiable function. Now twice differentiable just means that the second derivative exists. Like it's possible to take two derivatives of f. So the graph of a twice differentiable function f is shown below. Order the values f of 2, f prime of 2, and f double prime of 2 in order from least to greatest. F of 2 we can read right from the graph. F of 2 equals 0. F prime of 2 is the slope at 2. So f prime of 2, the slope of the graph at 2 is positive. So I don't know exactly what f prime of 2 is, but I do know that it's positive since f is increasing at that point. And then f double prime of 2, well, what's the concavity at 2? So at 2, the graph is concave down, and that tells me that the second derivative is negative. Again, I don't know the value, but I know it's negative. And I can put these three now in order from least to greatest because all negative numbers are smaller than 0, and all positive numbers are greater than 0. So we have f of 2 in the middle, and then our negative values to the left, so f double prime of 2 is the smallest, and then our positive values, f prime of 2, will be the largest. 37, the graph of f prime, which is the derivative of f of x, is shown below. So this is the graph of f prime of x. We're not looking at the graph of f, we're looking at the graph of its derivative. How many relative maximums does f have? Label these with a letter C. Well, a relative max is where f changes from increasing to decreasing. So it's where f prime changes from positive to negative. So where does our graph of f prime change from being positive to being negative? Well, here's positive, here it's negative. So right here, that would be a relative maximum. How many relative minimums does f have? Label these with the letter D. So a relative min is where f changes from decreasing to increasing. So it's where f prime changes from negative to positive. Now, where does the graph of f prime change from negative to positive? So we're negative here and then positive here. This is going to be a relative min. So that's point D. And right here as well. The graph is changing from negative to positive. The graph of f prime is changing from negative to positive. So that will be a min on the graph of f. How many points of inflection does f have? Label these with the letter E. Well, a point of inflection is where f changes from concave up to concave down, or vice versa, from concave down to concave up. Or we can say it's where the second derivative changes sign from negative to positive or positive to negative. But in terms of the graph of f prime, it's where f prime has a max or a min, a relative max or a min. So right here, the graph of f prime has a relative max, and that makes it an inflection point on the graph of f. Here we have a relative min. F prime has a relative min, so that means f, the original function, has an inflection point right there. And if that seems confusing, think about our first derivative test, our second derivative test, and what information we can get from that. So let's look at a second derivative test. If we have a second derivative test, then we want information, positive, negative information about f double prime. And we want increasing, decreasing information about f prime, and that tells us concavity information about f. Since we're looking at the graph of f prime, let's fill in that row first. So where is f prime increasing? Where is it decreasing? Well, it's increasing until we get to this point. So it starts out increasing, and then it changes and it's decreasing until we get to this point. So increasing, then it's decreasing, and then it's increasing. So the second derivative, positive, then negative, then positive, and f would be concave up, then concave down, then concave up. So right at these places where these signs change, we have inflection points. And where does that happen? Well, f prime is changing from increasing to decreasing right here where we labeled that point E. And it's changing from decreasing to increasing right here where we labeled our point E. Now, first derivative test, we would want sign information, positive, negative, about f prime, and that's going to tell us increasing, decreasing information about f. So since we are looking at the graph of f prime, we fill in that row first. Where is it positive? Where is it negative? Well, the graph starts out negative because it's below the x-axis. And then it's positive for a little while between where we marked C and D. then it's positive, then it's negative for a little while, and then it ends up being positive. So that means f is decreasing, then increasing, then decreasing, then increasing. So we want to identify where were those points where f prime changed from negative to positive, and positive to negative, and negative to positive. And those are going to be our relative maxes and mins. 38, the graph of f prime, the derivative of f of x, is shown below. So let's label that so we don't get confused. This is the graph of f prime, the derivative of f. What are the values of x where f of x has a relative maximum? We're looking at the graph of f prime. So we have a maximum on f wherever f changes from increasing to decreasing, and that's where the derivative changes from positive to negative. So where does the derivative graph, the f prime graph, change from positive to negative? Positive means above the x-axis, negative means below the x-axis. Well, looking at this graph, there are no places where it changes from being positive to being negative. So no relative maximums. What about values where f has a relative minimum? If f has a relative minimum, it's changing from decreasing to increasing. So the derivative, f prime, is changing from negative to positive. And that happens right here. The derivative is negative, and then all of a sudden it passes through the x-axis and it's positive. So right here at this point, 4, 0 is a relative minimum of f of x. On what intervals is the graph of f of x increasing? Okay, f of x increasing. So let's think about a first derivative test. So we have our number line. Critical values would be where f prime, this is the graph of f prime, wherever f prime is 0 or undefined. Well, f prime is 0 right here at 1, and it's also 0 right here at 4. So f prime is 0 in those places. F prime is negative to the left of 1. It's still negative between 1 and 4, and then it's positive from 4 to 5. We can go ahead and put our endpoints on here. So what does that tell us about f? Well, it tells us that f is decreasing, and then still decreasing, and then it turns and is increasing. So on what intervals is the graph of f increasing? That's wherever our first derivative is positive. So in the interval between 4 and 5. So we can say f of x is increasing on the interval from 4 to 5 since f prime is greater than 0. Part D, for what values of x does the graph of f have a point of inflection? And that's where the first derivative has a max or min. So I can see that pretty quickly by looking at the graph of f prime. But if you're not sure, point of inflection, think second derivative test. So second derivative, then we have f prime and then f. So second derivative, we want to know positive, negative. F prime, we want to know increasing, decreasing. F, we'd want to know concavity. Since we're looking at the graph of f prime, let's fill in the row for f prime. So f prime starts out increasing until we hit 1. And then it's decreasing until we hit 3. And then it's increasing after that. So going back up to the top row, if f prime is increasing, then its derivative, f double prime, is positive. And then when f prime is decreasing, second derivative is negative. When f prime is increasing, second derivative is positive. So what does that tell me about f? Concave up, concave down, concave up. And where the concavity changes, or where f double prime changes sign, we have inflection points. So we have an inflection point at x equals 1 and at x equals 3. F of x has points of inflection at x equals 1 and x equals 3, since f double prime changes sign. Or another justification you can give would be because f prime has a relative max and a relative min at those points. Part E, on what intervals is the graph of f concave up or concave down? Explain your reasoning. We've already done the work with our second derivative sign chart here. We can see where it's concave up and concave down. If we didn't make the sign chart and we were just looking at the graph of f prime, we'd want to know where is f prime increasing, that's concave up, and where is f prime decreasing, that's concave down. So we don't have to make a sign chart to figure this out. We can look at this graph of f prime. F prime is increasing until we hit 1, so we know f is concave up on that interval, and then it's decreasing until we hit 3, and then it's increasing after that. So we've got concave up on the interval -1 to 1 union 3 to infinity, and we can say since f prime is increasing. You can also justify that by saying f double prime is greater than 0. And then we have concave down on the interval from 1 to 3 since f prime is decreasing. Or you could justify that by saying f double prime is less than 0. Oh, and I just see where I made a mistake here. We do have distinct endpoints. So concave up from 3 to 5. It doesn't go past 5. Part F, if f of 3 equals 4, what is the equation of the normal line to the graph of f when x is 3? To write the equation of the normal line, we need to know a point on the line, and we have that. We have f of 3 equals 4, so we know that there's a point 3, 4 on the graph of f. Now we also want to know the slope. So I want to find f prime of 3. Now f prime of 3 we can read right from our graph because we have the graph of f prime here. So f prime of 3 equals -2. That means the slope of the tangent line is -2. So the slope of my tangent is -2, and that means the slope of my normal line, my perpendicular line, is positive 1/2. And then we can write the equation of the normal line. So it's y minus the y coordinate from my point 3, 4 equals the slope of the normal line, 1/2, times x minus the x coordinate of my point of tangency. So that's the equation of the normal line passing through 3, 4. Part G, if f of 3 equals 4, what is the tangent line approximation of f of 2.9? So now we need a tangent line equation. Well, that's easy to do since we've already done the work. For the normal line, our tangent lines, this is normal. Our tangent line has equation y minus 4 equals -2 times x minus 3. And then we're asked, what is that tangent line approximation of f of 2.9? So we want to let x equal 2.9 and solve for y. So if y minus 4 equals -2 times 2.9 minus 3. And there we get y equals 4.2. So the tangent line approximation of f of 2.9 is 4.2. Is this an over or under approximation? Well, for that we want to know the concavity of the graph when x is 3. Now that's going to be a little bit tricky in this problem. We have the graph of f prime, so we can see concavity of f by thinking about whether f prime is increasing or decreasing. But look what happens at 3. At 3, the derivative is changing from decreasing to increasing. That means the second derivative is changing from negative to positive. F double prime is changing from negative to positive. And so f is going to be concave down to the left of that point and concave up to the right of that point. So we're at an inflection point when x is 3. So let's think about the graph of f of x. When we're to the left of 3, the graph is concave down, and that means the tangent line is above the curve. It's an over approximation. If we're to the right of 3, the graph of f is concave up, so our tangent line would be below the curve and give us an under approximation. And since 2.9 is less than 3, we're in this scenario right here. F is concave down, so our tangent line is going to be above the curve, and it's going to give us an over approximation. Number 39, a function f is continuous from -2 to 4. We know that f of -2 is 5, f of 4 is 1, and we have information about f prime and f double prime in the table. At what values of x does f have relative extrema? So where do we have a relative max or a relative min? To answer that question, we're looking for a sign change in the first derivative. So where does f prime change from positive to negative or negative to positive? And f prime is positive, and then when we hit 0, it changes, and after that it becomes negative. So this is potentially a max or a min. Since we're told that the function is continuous, then there has to be a point there. F of 0 exists. And so we have probably a cusp or a corner at that point. So it is going to be a maximum because the first derivative changes from positive to negative. So we know f is changing from increasing to decreasing. So there's a relative max at x equals 0 since f prime changes from positive to negative. Part B, at what values of x does f have a point of inflection? So here we want to know, where does the second derivative have a sign change? So second derivative is positive from -2 to 0. It's still positive after 0 until you hit 2, and then once we hit 2, it becomes negative after that. So we do get a sign change in our second derivative here at x equals 2. So f has a point of inflection at x equals 2 since f double prime changes sign. On what intervals is the graph of f increasing, decreasing, concave up, or concave down? So for increasing, decreasing, we look at the sign of f prime. F is increasing on the interval. Okay, so here we're looking for where is f prime positive. So f is increasing on the interval -2 to 0. That's where f prime is positive, and that's the only place f prime is positive. So that's it, since f prime is greater than 0. F is decreasing wherever f prime is negative. So decreasing, we're negative here and here. So from 0 to 2, union 2 to 4. Since f prime is less than 0. And I'm splitting it at 2 because at 2, f prime is not less than 0, it's equal to 0. So if I include the 2 and just make it one big interval, then my reasoning isn't quite correct. Okay, and then concave down, f is concave, well, I guess we'll do concave up first. F is concave up on the interval. So concave up is where the second derivative is positive. So here and here. So concave up on the interval from -2 to 0, union 0 to 2, since f double prime is positive. And then f is concave down wherever our second derivative is negative. So that's this interval here from 2 to 4. Part D, suppose the equation of the tangent line drawn to f when x is 2 were used to evaluate f of 1.6 and f of 2.4. Would the approximations be under or over approximations? At x equals 2. So let's see what's happening at x equals 2. Here's x equals 2. At x equals 2, we have an inflection point. The second derivative is changing from positive to negative. So f, if I kind of add a little row here for f, f is going to be concave up just to the left of 2, and it's going to be concave down just to the right of 2, since our second derivative is positive to the left of 2 and negative to the right of 2. If the graph is concave up, that means the tangent line is below the curve. So when we're to the left of 2, the tangent line is going to give us an under approximation. So 1.6 is to the left of 2. F of 1.6 is an under, well, I'm saying that weird. The tangent line approximation to f of 1.6. It's a lot to fit in here. The tangent line approximation of f of 1.6 is an under approximation, since f double prime at 1.6 is greater than 0. It's positive, meaning concave up, meaning tangent line is an under approximation. And then we can say something similar for the other one. The tangent line approximation of f of 2.4, now we're larger than 2. 2.4 is to the right of 2. So this one is going to be to the right of 2, and the graph is concave down to the right of 2, so our tangent line is above the curve. We're going to get an over approximation. Is an over approximation, since f double prime of 2.4 is less than 0. And part E, sketch a possible graph of f of x. Okay, so I need to jot down some of that information we've already found. Well, first of all, we know f of negative 2 equals 5. That's given. F of negative 2 equals 5. So we have f passes through this point here. F of 4 equals 1. So we have another point right here. Okay, then to summarize the information we've already figured out, let's just do a sign chart, a first derivative sign chart and a second derivative sign chart. We had critical points at 0 and 2. So the first derivative did not exist at 0, and it was equal to 0 when x was 2. And then it was positive, negative, negative. Okay, so what that tells me about f is that it's increasing until 0, and then decreasing between 0 and 2, and then still decreasing after 2. And then let's do a second derivative sign chart. Critical values here were also 0 and 2. So the second derivative also did not exist at 0, and it was equal to 0 at 2. But our signs were positive, positive, negative. Okay, so that tells us first derivative increasing, increasing, decreasing, and f concave up, concave up, concave down. Okay, so let's try and sketch our graph. We know f is increasing and concave up until we hit an x value of 0. And then the derivative doesn't exist. So I'm going to draw it as a cusp. And we'll do something like that. So it's increasing, concave up. I got a little bit wobbly over here, but increasing concave up until we get to 0. And then decreasing but still concave up until we get to 2. And concave up until I hit an x value of 2. And then we're going to continue decreasing, but we switch to being concave down. Okay, so we have an inflection point when x is 2. Concave down on the left, or no, I'm sorry, concave up on the left, concave down on the right. So let's run through this one more time and make sure everything works. So from my first derivative chart, I should be increasing until I hit 0, and then decreasing after that. So that works. From my second derivative chart, f should be concave up until I get to 0, and then derivative doesn't exist, but still concave up after that, and then we switch at 2 and we're concave down. And then last thing, I should have paid attention to my domain. It goes from negative 2 to 4, so we don't have any points on the graph to the left of negative 2.